Welcome to chapter 11. As you can see, this chapter is all about gases. So we'll get started right away. The first thing we're going to talk about is just a bunch of different properties of gases. The first thing you need to know is they have very low density. You probably already knew this. But they typically have about 1/1000th the density of their liquid or solid counterparts. So as you can see, here's an example. The density of oxygen as a gas is about 0.001429 grams per milliliter. That's at 0 degrees Celsius. The density of oxygen as a liquid is about, you can see it's very close to 1,000 times bigger than that. So densities of gases are about 1/1000th that of their liquid or solid counterpart. The other thing about gases is that they do expand. They expand significantly when their temperature changes versus like solids and liquids. Yes, there is a little bit of thermal expansion, but it's a very, very small percentage of their current volume, right? We know that solids and liquids do expand a tiny bit, but gases will expand significantly when they get warmer or colder. So they don't have a definite shape or volume. So that means they take the shape and the volume of the container. Whereas like a liquid will take the shape of the container, but it will always occupy, the bottom part of the container. It doesn't expand to fill up the entire container. I have a water bottle that's half full. The water sits on the bottom half. Versus if I have it full of gas, the gas will evenly spread out throughout the entire container. So they expand to fit their container. The other thing about gases is that they can be compressed. Solids and liquids, they can't be compressed, whereas gases can. So we have a little animation here. You can see if you have a cylinder and a piston, there's a lot of space between gas molecules, so that means if there's a lot of empty space, you can move that piston and just kind of decrease that space a bit. As we'll learn in a future video, when you do decrease the volume of a cylinder like this, the pressure inside of it's going to increase because those gas molecules are hitting the container more often, or the edge of the container. So that's why it says right here, as you compress it, the pressure will change. Another thing, gases are considered fluids. A fluid is not just reserved for liquids. Gases are also considered fluids because they can flow past each other. They can change their shape easy. And we also assume that there's no interaction between gas particles. So when these particles are bouncing off of each other, they don't really stick to each other. There's no attraction between them. They bounce off with perfect elastic collisions, which isn't fully true, but we make that assumption to use the equations that we're going to use in the future. And it's close enough to being true that it works for our purposes. Diffusion, another word you need to know. If you have two gases here, they're separated. I have gas A and gas B. If I remove this wall that's between them, they're just going to naturally spread out and fill the entire container. So that's what diffusion is. So they will spontaneously mix due to random motion. Realize I'm missing a parenthesis there. So you don't have to stir them. They'll just randomly mix up themselves. The same thing if someone were to spray some perfume in one corner of a room. You don't have to mix up the room to know that, or mix up the gas in the room to know that someone across the room will eventually smell it, because those gas molecules from the perfume will slowly diffuse across the room, and you will be able to smell them because they mix throughout the entire room. They'll spread out and randomly and evenly mix throughout the entire room if given enough time. The next one is effusion. This is where gases escape through a tiny opening. Again, gas molecules are always randomly bouncing around, bouncing off of each other. And so that means if there's a little opening here, you're always going to have at least a few gas molecules that line up, and their motion happens to send them out that tiny opening. That's why if you get a small hole in your tire, the gas will slowly escape out of that because the random motion, you're going to have molecules that are randomly bouncing through that hole and then escaping. So make sure you know the difference between effusion and diffusion for the test. Some other properties of gases. Pressure is force per unit area. So how much force is being applied to a given area. Now force is measured in newtons. That's the typical unit we use for forces in the metric system. Meter is the base unit of distance. Sorry, I got interrupted there, so now I'm back. We've got, I believe I was at forces in newtons. Base unit of distance is meters. So we got force per, or newtons per meter squared, which is 1 Pascal. But if you think about this unit, a newton isn't that big of a force, and a square meter is a very large force. So a Pascal, while it's a typical unit for pressure, it's not used all that often because it's such a small amount of pressure that you end up working with huge numbers. So a more common unit that you'll see is kPa, which is kilopascals, which is 1,000 pascals. But even that, when you work with pressure in your daily life, you probably are looking at a pressure gauge like this. You're looking at pounds per square inch, which is PSI. And there's so many units for pressure that we're not going to worry too much about it. Just know that there's a lot of different units, and we'll talk about a couple, but there's a lot more out there that we don't really have to worry about. So let's continue on. Okay, so a device that's used to measure pressure is called a barometer. This is an example of a barometer over here. What happens in this is that you fill up in a tube that's closed on one end but open on the other end. You fill it completely with mercury, invert it into a tub of mercury, and now mercury is really dense and heavy, so the weight of the mercury wants to pull it down. Gravity wants the mercury to fall out of the tube, but then that creates a vacuum up here because there's no gas up there. So now what you have is the weight of the mercury pushing down, but you also have the weight of the air out here that's pushing on this tub, which tries to push the mercury back in. So when those two forces equal each other, that tells you the atmospheric pressure. And you can measure the height of this mercury column. Typically, atmospheric pressure is 760 millimeters. The height of this column would be that distance. So that's why millimeters of mercury is actually a pressure unit, or inches of mercury is another one. Now, as the pressure drops or increases due to weather, if rain's coming, you usually get pressure dropping. If the force outside here gets lower, the atmospheric pressure drops. That means that the weight of the mercury will fall down a little bit further. So then this number decreases. The pressure outside increases, that pushes more mercury into it, which increases the height, and so that registers as a higher atmospheric pressure. So that's one way to measure pressure. So this guy, Evangelista Torricelli, he developed the barometer. So the unit 1 millimeter of mercury is also called 1 torr. And I already warned you, there's a lot of pressure units. They are hard to keep track of. You don't have to worry about them too much. We're mostly going to work with atmospheres when we get to calculations. So that gets us to atmospheric pressure. That's the pressure of the gas pushing down on you, which is surprisingly large that you don't think about. So the average pressure at sea level at 0 degrees Celsius is 760 millimeters of mercury, or 760 torr. We also call that 1 atmosphere of pressure, which makes sense, right? We have 1 atmosphere above us. That's our Earth's atmosphere. And so Earth's atmosphere is 1 atmosphere. If you want to talk about it in PSI, that's 14.7 PSI. And this is where I told you pascals are really small. So it's 101,300 Pascal, which is a big number, and it's kind of annoying to work with those big numbers. So that's why pascals isn't used very often. But if you think about that, in your body, or on your body, every square inch, there's 14.7 pounds pushing on it from the air pressure around you, which is quite significant. So here's a little graphic to show you how air pressure works. So the molecules of gas that you breathe in, they have mass, and gravity pulls on those molecules just like they do everything else, which pulls them down. And if we're down here, there's actually a lot of gas above us that has a lot of mass and a lot of weight. So that does push down and creates a pressure So surface air pressure equals the weight of an air column above that unit of area. So on the ground is actually holding up the gas molecules that are pushing down on it. And then those gas molecules hold up the gas molecules above it. They hold up the gas molecules above that. Then as you get further and further up, there's less total weight above it, so the air pressure decreases as you go up higher and higher altitudes. That's why if you go hike in the mountains, you might go up somewhere here where there's just less gas molecules. So when you breathe, you're intaking less oxygen and less everything, all the gases that are in the atmosphere, and it can be harder to breathe, and you really feel out of shape because you're not taking in as much oxygen, and you'll feel out of breath. So that's just another example of air pressure.